Good. Our topic for the second half of this session today is a general introduction to deep learning. And what you see in front of you is a feed-forward neural network. It's something that we have already seen in the previous classes. So you've got an input layer of neurons followed by one or more hidden layers followed by an output layer. Is what you see. And what each of these layers does is it'll do a linearity. It'll do a linearity over the input space primarily, like it'll compute what is typically represented mathematically as double transpose X, and then you apply non-linearity using an appropriate activation function. So the neural network essentially what it does is it's a collection of linearities followed by non-linearities. That's what we are seeing, right, in the case of a feed-forward neural network. So W transpose X, and which is passed on to an activation function F. So F of W transpose X is what is being computed at every layer, and it keeps pushed up in one direction. That's in the forward direction from the input to the output. That's called a feed-forward neural network. And how do you train the parameters of such a model? Right. What you see in front of you is basically the output will be any moment with W transpose I plus W transpose X. So this is essentially the plus B will be the linearity followed by activation, which is non-linearity. Right? So if you look at the feed-forward neural network, what is being shown over here is you can see that. So this is a simple network with one input layer, another output layer, and a single hidden layer. Right? How many parameters? And you train such a network using the algorithm. Generalized delta rule or grading is a procedure called backpropagation algorithm. So in backpropagation algorithm, what we have seen is you present the input to the network and you push it through the layers, and finally you get an output. Once you get an output, you compute the notion of error, and once you have the notion of error, you compute the gradient of the error with respect to the parameters of the model, and then the gradient is is pushed backwards in the backward direction to adjust the parameters, primarily the weights of this network. And that procedure is called the gradient descent procedure. And the procedure in the case of feed-forward neural network is termed as backpropagation algorithm, which can be expanded to backward propagation of the error gradient. That's what the algorithm is. So this is how you train the parameters of a feed-forward neural network. Good. Let's look at the parameter space of this model. In the parameter space of the model, if you look at it, this is a fully connected, meaning like everybody is connected to every input is connected. Every input node is connected to every other neuron in the hidden layer, and so is true with the connections between the hidden and output layer. Right? You can see like 4 plus. So basically, like if you look at if you're not considering, this is basically the presentation of the input, so you don't normally count it. So you have got 4 plus 2, not counting the input, you have got 6 neurons. And how many connections you have? 3 into 4, basically 12 connections over here. And 4 into 2 is basically 8 connections. So there are totally 20 connections. And each of the 6 neurons will have appropriate base biases also. So we have 6 biases. So the tunable parameters of this model is 20 reads plus 6 biases. So there are 26 learnable parameters. So if you keep adding more and more layers to this network, what is going to happen is you will have a lot of parameters, right? If you have got 5 over here and 3 over here, you would have 15 instead of 12. So you can, as the number of layers increases, as the number of neurons in each of the layer increases, the parameter space keep on increasing. And feed-forward neural network, in the case of a feed-forward neural network, we have a mechanism to learn the parameters, which is gradient descent. This is just a recap of what you've done. All right. So the training is essentially like forward presentation of the input, basically like forward presentation of the signal, and then backward propagation of the gradient. So that across the error curve, we are trying to look for that set of parameters which will minimize the error. Right. That's what it is. That is what is the agenda for backpropagation algorithm, which is gradient descent procedure applied in feed-forward neural networks. Good. So what's the difference between ML and DL? Machine learning and deep learning. That's a primary question that people ask, and this is the simplest answer, right? So in machine learning, what we do is we always depend on human design representation of input features. I told you about a famous theorem called ugly duckling theorem, maybe towards the earlier part of the course, where I said ugly duckling theorem. What it says is there is no context independent representation. The best representation cannot be context independent, or the representation which is a valid representation which cannot be context independent. If there are many ducklings in a group, and one of the duckling do have a slightly deformed beak. All right, the beak is deformed, and you don't use the beak as a part of your representation. You only represent its color, wing, weight, etc., etc., and you don't consider beak at all unless you represent beak. The duckling where whose beak is slightly deformed will be equally beautiful like any other duckling, right? So this particular theorem which says unless otherwise you have a context which says you need to capture the notion of that ugliness in a particular, or distinguish between ducklings which are labeled as ugly or otherwise, unless you capture that feature or aspect which has that particular element in it, you will not be able to distinguish, or you will not be able to do your job in a what you call satisfying manner. So what I want to say is ugly duckling theorem is essentially a statement which says there is nothing like duckling which is ugly unless otherwise you capture that feature which essentially has that ugliness as a part of the context. So that's what the ugly duckling theorem is all about. So there is, in the case of machine learning, we presume that your data is always well represented. You have the right feature representation, and that's why, like when you look at representational engineering, we have seen things of the kind feature engineering, which is feature selection, feature reduction, or feature extraction kind of methods. You see that you always when you have to apply a machine learning algorithm, you presume that you have the right data representation. All right, and but deep learning, you don't have to presume that. You can present what you have in hand and let the representation be also learned. Right? Can you learn the representation? So deep learning, in a perspective, you can see that deep learning is more to do with representation learning, and then followed by an appropriate machine learning based decision making process. So that's how deep learning is typically perceived. So machine learning practice describe your data features is very in a fashion which captures your problem context, and then there's a learning algorithm. That's what machine learning is all about. So you have in the case of a text classification problem, you say, okay, I'll have the features like the current word, the previous word, next word, etc., etc. You can represent a lot of things. And if you want to do an email classification context, you need to well represent. You may use a TF-IDF kind of representation. You may use a word vector representation. You presume that you have the right representation, and then you attempt the problem. But in deep learning, you don't have to. Basically, it says like you can do representation learning also. So machine learning is learning. It's basically it's a field of learning. It's a field of learning where machine learning, you presume you have the right representation, but in the case of deep learning, rather than you having the right representation of data, can the machine figure out the right representation by an appropriately placed hierarchy of learning abstractions, and then you finally end up with the final classification. Say, for example, in the case of machine learning, if the car is your input, so you have to do the right feature engineering, and then there is a learning algorithm which uses these engineered features, and then the final problem is solved. In the case of deep learning, it's originally started with deep neural networks. Don't think that deep learning is happening only in neural networks. It also happens in machines like kernel machines, and people like us work on deep kernel algorithms or deep kernel architectures. So originally, deep learning emerged in the area of neural networks. You may have a representation of a car represented. Basically given to you as description in 50,000 words, and this can be taken up by the network, and from the words it may be able to identify correct abstraction at some layer, and with that layer there will be decision making. So you don't have to have feature extraction tools, whatever classification or the current, we are giving the example of classification, can be regression or it can be clustering or whatever. So you don't presume a proper feature engineering in the case of deep learning. Rather, the network will learn its own required set of features from the available data. Right? That's what deep learning is all about. So deep learning does, to a large extent, representation learning. All right, a traditional pattern recognition machine learning, all right, feature extractor and then trainable classifier. Means the modern pattern recognition machine learning, what it does is feature extraction, then mid-level features. Say you do something like a PCE and then a classifier. Right? Deep learning says, hey, you have lower level representation, you have descriptions and then mid-level features, high-level features, and it will do all sort of feature engineering, and then there's a machine learning based on top of it. We're going to see how does it happen in a neural network. That's what the agenda for today. And like machine learning, deep learning also has different paradigms. It has supervised learning approaches like a convolution neural network or a vector neural network, and supervised learning like restricted Boltzmann machines or RBMs, which essentially like find representation of data using what is called autoencoders. This is where most of the deep learning literature started, and of late there are reinforcement learning approaches also, deep reinforcement learning, to be very precise, deep learning, which was applied by DeepMind in solving the AlphaGo problem. So basically the AlphaGo system, basically the what do you call the software that played against the best Go player, and the AlphaGo program used a reinforcement technique called DeepQLearn. Right? So all these kind of flavors which exist in machine learning also is present in the deep learning literature, and we'll be mostly around this, working around this. And a lot of resources available, so everything is scanned and given to you. These are some of the some of the stuff that I've just captured, but these are not the only thing we'll be using Keras today, which is not, I think I have not listed Keras over here. We'll be using TensorFlow, right, and a framework on top of it called Keras to do some experiments over here. All right, why DL is useful? Because feature engineering is not an easy task. Many manual design features are often overspecified, incomplete, and there's a lot of human creativity involved in designing the right set of features. Learn features are easy to adapt and fast to learn. So deep learning, because you don't have to do feature engineering, rather the system, the algorithm itself figures out what to be identified. All right, so they call it flexible, they call it universal. Yeah, these are even though they are debatable terms, this is how the world perceives it. We can learn both, we can apply both supervised and unsupervised approaches, and they can utilize a large volume of data, because see, the feature engineering when automated or representation learning when automated, it's not real. Right? Let us look how the neural network, which was the original incarnation, which is where the original incarnation of deep learning came into existence, how neural networks are capable of learning features. Right? I told you machine learning is all about well-engineered features followed by a learning algorithm, and deep learning is all about the representation can be learned, and then there is a learning component, basically the decision-making component placed, and then it does a job. Right? How the neural networks are capable of learning features is what I wanted to tell you, because once you understand this further, the semantics, deep learning becomes, the theory of deep learning is more or less trivial. All right, let us look at a digit classification example. This is an example again I've taken from the available literature, just to give you an overview of how the neural networks are capable of doing feature and basically representation learning. All right, this is a digit classification, handwritten digit classification problem, and you must have seen by now problems like the MNISTs of this kind. All right, so you have got digits over here. So 0 to 9 are the digits, and multiple examples, training examples, and the corresponding training example, meaning your data along with the labels are available, and the digit will look like this. Say, for example, it's a 9. All right. So when you're presenting your 9, so if you assume that is a 8 by 8, it's not 8 by 8. So this may be like how many are there? 3 plus 3, so 7 and 1, 2, 3, 4, 5, 6, 7, 8, 9. So basically 7 by 9. So this basically 7 into 9 will be the number of dimensions over here. So when you are presenting this 7 into 9, what is that? So 7 into 9 values to this network. So when you present, say this first value is 0, this is 0, the third one is also 0, but the fourth one is a 1, fifth one is a 1, maybe like sixth one is a 1, and likewise some other values are 1. So you are presenting your input layer with a sequence of what you call sequence or essentially like a pattern of zeros and ones, right? And this being so these are the weights connecting the input to the hidden layers. All right. So if this is a 0, end up what do you call it? Whatever be the weight over here, all these connections will carry a 0 here. Right? Will give a 0 here, 0 output over here over this network. All right. So which means that some of these weights will be like some of these connections will be on and off depending on what you present over here. And if you keep considering this, so basically when you're presenting a pattern to this input layer, what is happening is you're switching on and switching off some of these weights. That's essentially the pointer. All right. So basically, like some of these weights are on, some of these weights are off. All right. And so strong weights versus low or zero weights, right? That's what it is. It will send strong signals for a horizontal line with where there is what you call ones on, and otherwise it'll be off. All right. And if you keep presenting what you call, so what do you do with the network? You keep presenting your what you call your data to this network. Say 9 comes in, 5 gets in, 4 gets in. So meaning some of these ways will be on off, etc. And what does these things capture? This is basically like, see, when a 9 is presented, some of these will be either these things can be on, off, or whatever. Right? 5 is presented, some of these things can be on, off, etc. And 1 is present, some of these can be on, off, etc. So from this layer, the input layer to the hidden layer, the first hidden layer, what these fellows specialize is essentially they are able to capture. So these weights are essentially like when you adjust the weights according to these presentation of inputs and what you call, I mean, so your weights are also gradient into the input, right? That's how you update the weights. When these weights are actually learned, what you essentially do is you will find these will specialize on certain dimensions, right? So this will say, okay, when these weights are on, these weights are off, my weights are adjusted in such a way that I am able to capture some abstraction of the input. This next neuron also will find some abstraction of the input. The next neuron will also find some abstraction of the input. All these neurons in the hidden layer will find some abstraction of the input. And the layers up here, maybe like the next hidden layer, they will get input from here. So when this is on, some of this will be on, right? When this is off, this will be off. So each of these neurons will specialize on certain abstractions, what you call, which are learned from the layers below. So look at this in our case. Say for example, hidden layers of unit are self-organized feature detectors is what is essentially happening. That's all I wanted to say. So essentially, when you present a pattern, right, pattern which is essentially an input to this network, what is happening is like certain things will be on, certain things will be off, and based on that, the higher level neurons will become specialists for finding certain abstractions of the input layer of the input being presented. So some neurons may learn vertical lines, some neurons may learn horizontal lines, some neurons may find small circles, because see, their weights will be oriented in such a way that, see, when you are presenting this input, come back to our original figure. When you're presenting this input is essentially decide what will be the weights over here. Once these weights are learned, if these weights are low, meaning only some part of the input will go here. If some of these weights are zero, meaning the input will not will not be accepted, will not be basically like, what will be the, even if these are ones, that input will not be seen by this network. Essentially, once these weights are learned, which in turn are depend on the input being presented. See, these weights are essentially like, when you look at these weights vectors, you can see that these weight vectors will have this kind of a form. So essentially, based on the input, what you call, the weight vectors will be accordingly, like we'll get some values of the weight vectors, some will become strengthened, some will become, what you call, this is for a neuron in the hidden layer, at some hidden layer. So for example, let's consider the neuron over here. So some of these weights actually, like depending on the input being presented, the weights go through a transformation, and essentially what the weight vector goes through a, what you call, learning process, and essentially you end up in certain weights which are very positive, which are low, zero, etc., etc. Essentially, when the network is presented with a new test input or new input, depending on what these weight vectors are, this neuron will see only certain parts of it, will not see the rest of the things. That's what it is. So if you look at here look at also, see, when these weights are essentially learned and what you call and fixed out there, you will see that this neuron will see only look for certain patterns within this layer. All right, this neuron will look only for certain patterns. If this is there, if there is a 1, that will be seen. If there is a 0, that won't be seen. If there is a 1, that will be seen. Say all the hidden layer neurons are essentially like feature, basically like, will work as feature selectors. Essentially, you can see that these are learning abstractions of the features. So a strong positive weight will detect what you call the corresponding feature. If the corresponding weight is 0 or low, it will not detect that feature. So strong signal for a dark area and low signal for a whatever, basically of a particular, even if what you call, say this is dark, if your input is dark, if this weight connecting that neuron to that input dimension is low, this won't be seen. Basically, if it's 0, it will be like kind of what you call it, ignored. So back to our thought. So the higher level neurons are essentially can detect what you call a 1, can detect a horizontal, or basically it can detect a vertical line, it can detect a horizontal line. Some neurons, based on its weights, may only look at points where there is a small circle. So successive layers can learn higher level features, is what I want to say. So based on the input presented, the weights will get updated. Based on the weights are essentially like for any neuron, its weights will decide what it sees. It will see only certain things, it will not see everything. The weight won't be like, will not be, a high for every other connection, right? It will be low somewhere, high somewhere, 0 somewhere, etc., etc., etc. Which means that every neuron in the hidden layer, at any layer, will be looking for certain patterns in its input. So certain neurons will detect horizontal lines. Say, for example, it may detect a horizontal line over here. Certain other neurons may detect vertical lines. Certain other neurons may detect circles, etc. So every incremental, what we call, layer in the hidden part of the network can essentially be treated as feature detectors. All right. So if you look at this particular network, we can see that some of these neurons, this may detect a corner, corner curve. This neuron may detect a slight curve out there. This may detect a straight line. This may detect a curve downstairs, etc., etc. And from here, this curve and this neuron and this neuron, if they are connected, the curve and the curve and the upper layer may be combined to form a higher level thing here. So 9, if you look at 9, say some neuron at the first layer may detect this, some may detect this, some may detect this, some may detect this, some may detect this, and maybe like higher level neurons, somebody may make a structure like this, somebody else may make a structure like this, somebody else can make a structure like this, and the layer above, if there is a hidden layer here, this may combine this and this to form a circle, and maybe a higher level thing will combine that circle and a straight line to form a 9, right? Essentially, and that 9 becomes what we call, and then there is a label out there. So the 9 is labeled as 9. So this is how things are happening here. So all I want to say from this particular picture is successive layers can learn higher level features, right? So multiple layers. So this layer may detect pieces of the structure depending on the weight that it learned. From these feature set, this layer may detect the higher level features, and likewise, and ultimately you will have a decision making layer. All right. So what we call a deep neural network is essentially can do feature engineering like this, and this is how your brain works, and that is the what we call the contribution that the scientists in the deep network or deep layered neural network context have identified, and that is how this is the basic philosophy behind building what we call deep neural networks, right, or deep learning. This is how deep learning emerged. So if we can create arguably deep networks which can do incremental feature, which can essentially find incremental abstraction of the features, you don't have to provide well-engineered features and of well-engineered featured well-engineered feature set at the input. Rather, you can provide what you have in hand, and then incrementally this network will be able to detect higher level features and then keep going from there. And that is where deep learning was born. The entire context of deep learning was born. They said, hey, let's not do what we call well-featured feature engineering, well-represented feature engineering. Rather, let us build deep layered network where each of the higher level can find a higher level abstraction, each of the deep layer can find a higher level abstraction of the data. And then let's do that to a context where the feature is basically well enough so that the final classification is good enough so that the final classification can be done. Right? This is how the deep layered network doing deep learning emerged. All right. So all I want to say is, so this can be a textbook with all your input is only characters. So this particular network may identify what we call, may combine characters to form words. This layer may combine words to form sentences, and this network may form words to form phrases, and this network may form what we call phrases to may combine phrases to form sentences, and then sentence level classification may be done here to do whether what we call the sentence is actually a positive sentence or a negative sentence to a semantic what we call not the sentiment analysis. So the entire thing is a sentiment analysis problem. You don't do a word to vector engineering, or you don't do all that. Rather, you can use text at the input layer, and the incremental what we call feature engineering is done, and finally the what we call the sentiment analysis problem is solved with only text given as input. So this can be a picture. We'll see one example there. This can be a picture. The picture is represented in terms of the pixels that represent the picture, and the pixels are combined to form small what we call small curves or small shapes out here, and then these small shapes are combined to form larger what we call larger shaped curves or whatever, and curves are formed to form well-built modules. And finally, the classification problem is like a house versus a car. The problem is a house versus a car. So these the what you call the building blocks that this network will make for a car will be different from that of a house, which means that the final classification part of the network is basically the final decision making part of the network will be able to do a reasonable job. Right? That's what it is. That's what's happening in the case of a deep layered neural network. Right? Let me show you how you build such a network. Is it very difficult to build such a network? I'll show you I have a collab, what you call context here. Let me open collab. I hope some of you might have already started. I've created a collab, what you call example, just to show you. So it's let me load this. I hope you can see this. So this is an example that what it does is like it takes a standard data set and it uses the Keras library, which in turn uses TensorFlow. So I'm using Keras library just to collab is essentially the Google provided what we call collaboratory. where you can write code. And this is a Python notebook that I've created in Colab. I've imported all the libraries, and all I'm doing is there is a data set which is coming along with the Keras, which is called Fashion MNIST data set. This data set has 60,000 training points, training images, and the corresponding labels. Labels are essentially is a 10 class classification problem. Labels are it's actually images of what do you call apparels, and so we have labels such as t-shirts, trouser, pullover, dress, coat, sandal, shirt, etc., etc., and etc. So so there are 60,000 training examples, so 60,000 images with the corresponding label given, and there are 10,000 what do you call test images, and each of these images is a 28 by 28 pixel. Is represented in a 28 by 28 dimensions, so 28 into 28, 784. So that will be the dimensionality of the input space. So, and this data set, what I'm doing here is I'm just loading the data set from Keras. So let me run. This is a Python notebook that I've created. I'm just loading this data set from Keras. Let me show you. It's taking a little time. So it comes with Keras. You can also I'll share this code. So the data set is loaded from Keras. So you can see that 60,000 what do you call training samples, each of 28 by 28 dimension, and 10,000 tests 28 by 28 dimension. So what I want to do is, and the class labels are like this. So we have just taking the class labels out here, and let's do a plotting. It's nothing but a plotting. So let's do a plotting of this data set just to see like how does it look like. Again, I've taken a public repository, and so data set goes like this. I've just plotted 10 examples out of this 60,000 things. I've taken 10 examples. So these are 28 by 28 dimensional thing, which is an angle board with t-shirt. These are the training labels, and these are the actual data. X this is X, and this is the corresponding label Y, right? X and Y. So I got 10, I plotted only 10. So I got 60,000 training examples, and we'll just what do you call convert it into what do you call the values between 0 and 1. Basically, divided to convert the image into the gray scale, and then this is how I've constructed a small. So I've created a sequential Keras model. Essentially, I'm creating a small network with 3 layers. The first layer is a flattened layer. Flattened layer is you have got 28 by 28 dimensional what do you call images, right? 28 into 28 plus bias, so 785. So your input will be converted to 784 plus 1, 28 into 28 plus 1. That'll be that's the purpose of this layer. And the next layer is I'm using a densely connected network, meaning like everybody is connected to everybody else. So I'm creating a dense network with 128 what do you call neurons. And activation and that I use there is ReLU max of 0,1. And the final layer I use is basically again with since there are 10 classes, I'm using an output layer with 10 neurons, and the activation function used there is softmax. So this is essentially defining the model. I just define the model, and then I'm compiling the model. Essentially, I create the model, and I am trying to train that with the training data available. So I just let me train this network. Right, I've created the neural network, and I'm trying to train it so I'm giving 10 epochs, meaning data is presented 10 times, and batch size every time it takes 60. And so basically I do a cross validation. Cross validation is essentially like when you have it's 20% cross validation. So what you do is so at any moment, in order to train your parameters, your training data is split into what you call the train part and a validation part. So when you say point to what is happening is like 80% of the data is used to train the parameters, and I'll do a testing over this 20% of the data. And then if there is like we do the parameter tuning over this 20%, and this 20% they keep changing, randomly taken 20% over these epochs will be taken for parameter tuning. So if everything is done, it's finished, and then let's evaluate the model over the test set. That's 10,000 points, and it gave me an accuracy of what you can look at it. Accuracy is 87. Let me look at some of the predicted labels. I'm taking randomly some 10 points on the data, and then trying to what you call predict the label. This is actually the label, the actual label, and the predicted label. This is trouser, which is predicted to be a dress. Shirt is predicted to be a shirt, and shirt. So everything is not right. Something is wrong. Some things are right. Sandal, sneaker, sneaker, lower. Let me do another random test. I'm randomly scanned that time. So this everything is coming properly here. T-shirt. T-shirt is predicted as a shirt. Dress and dress. Pullover is predicted as a shirt. So we get to 87% accuracy. So all I want to say is, don't worry. I'll share you this code also. The Python notebook, and you need to create what you call your assignment will be on the same lines. You have to create a Python notebook. You can do it either in Colab or you can do it in Jupyter notebooks. Both are fine with me. So, and you need to share that, and that will use for your what you call it. You will be asked to present, or you may even publish it in a public forum. So all I want to show here is my entire what you call that, creating a deep network. So I have created a network with a network with 3 layers over here, and the entire, see, the moment you have a library of this kind, your job reduces to like creating that model graph, and then compiling it and fitting into the training data. And so it's so simple. That's all I want to say here. So good. With that, I'll move on. I'll move on to my original slide set. All I want to show over here is from this entire discussion on deep neural networks. So essentially, the deep learning in neural networks is essentially about creating a deep layer network. I've shown you how to create a 3-layer network. If I want to add multiple layers, since I've got libraries of this kind, life is pretty straightforward. What happens in a deep layer network is these weights are essentially feature selectors. So each of these neurons in the hidden layer are essentially specialists capturing certain aspect of the feature, and higher level neurons will specialize on higher level features. And likewise, ultimately, you get to a layer where you take the ultimate decision. Right? This is the basic idea behind deep learning in neural networks or deep structured neural networks, and your brain works that way. Right? And with that note, I want to stop the introductory part of the deep learning. Right? Let me show you a simple neuronal model which does a little beyond this. We'll look at what you call the introductory part of a network. I don't want to of a network which is appealing for the eyes. So that's the reason why I wanted to start with a convolutional neural network. Right? Let me show you convolutional neural network, which is one of the most celebrated networks in the deep learning world. This is, to be very precise, this network is used for spatial signal processing, and we'll see another network which is originally designed for sequential data processing, or basically like sequence modeling. This is used for space modeling and finds a lot of applications in the image processing world, image classification and related things. And there is a celebrated problem around this, the image classification context, which is called ImageNet problem. I want all of you to go back and look at the ImageNet problem, and a lot of networks have come out in these class algorithms. So let me give you an overview of what a convolutional neural network. This is again a deep layered neural architecture, how a convolutional neural network works, right? And supervised learning paradigm, traditional supervised learning paradigm, I told you already, handcrafted features, trainable classifier, output. This is machine learning, right? Deep learning has an inbuilt automatic multi-stage feature learning process. I told you, like the incremental layers can learn higher level features, right? Lower level features to mid level features to high level features to, then there is a trainable classifier, and then there is an output. So this is where the actual ML part of the deal happens, right? Till this point, this is feature engineering, right? Learning the right representation of the data, right? That's what is happening in deep networks. All right, and to give you a little more context, I think this would help. Say your input may be represented in terms of pixels. So from the pixels, the edges may be detected by the higher level network, higher level neurons. Texture may be detected further up, motifs, parts, objects, etc. So basically, like this is what it comes from the image processing literature. You can go look at it. Text can be like your initial representation, as I've already told you. Initial representation maybe in terms of characters. Higher level network may identify words, then word groups and clauses and phrases and sentences and probably stories, and your actual classification may happen at a story level. This is possible. Right? This is what is happening. So a simple neural network, I mean, see, basically once these weights are learned, all these fellows are essentially what they do is they are specialists of specialists looking into certain aspects of the input. Right? An artificial neural network is an information processing paradigm that is inspired by the biological nervous system, and incremental layers can essentially do higher level feature engineering. Right? So a simple neural network, you can see that, I mean, I've told you a neural network is essentially linearity followed by any layer. What it does is linearity followed by non-linearity. So at the A1 layer, the first layer of the network, A1, you can see that A1 can do like kind of W1, A2, X1, etc., and then there is an activation. F is activation function. So if it's a ReLU activation function, what you essentially get is something like this. Right, this layer can essentially do depending on what these WIs are. So this will see something, this will see something else, this will see something else differently, and so these are all features. And ultimately, you can, I mean, see, this is a network with a single hidden layer, input layer, hidden layer, and output layer. Output is essentially, you presume that's a softmax layer. Softmax is essentially like they function like this: 1 plus 1 by e raised to W into A1. So it's, I mean, you must have seen this the structure of this function, right? Have you seen this? Okay, so softmax function is this. So you can do a softmax is over the input space, and then you decide what to be done there, right? And originally, back to our original thought. So if there are what we call 4 things here, there'll be, and 4 inputs. So 4 into 4. So basically 16 over here, 16 weights over here, and the parameter space would be, and output has only 1 layer, so which means that 4. So 4 into 4 plus 4, 16 plus 4, there will be 20 weights. And how many biases? If there is only 1, then there will be like kind of 1 plus 4, so 5 biases. So 20 plus 5, 25 parameters will be there in this neuron, in this particular model. All right. If it's an input image, let's assume that this is an image, this is an input image, this is a typical or your training data. I mean, the points in the training data looks like this. And let's assume that this is a 400 by 400 dimensional image with 3 channels, one for each one for R, G, and B. It's basically a color image, right? RGB. So basically, for the primary colors, there is a channel. So there is these 3 comes in. So 400 to 400, and you have got 3 channels for the 3 primary colors. So 400 to 400 to 3, that will be 16 into 3 is 48. What do you call it? It's basically so 48 into 3 and with 4 zeros. So it'll be like 4,08,000, right? 4,08,000. So if you flatten this data out here in a picture, it'll be 4,80,000 dimensional. What do you call it? Dimensional will be the dimensionality of the input. And if there are what do you call? I mean, how many, like if we are keeping 4,80,000 neurons in the hidden layer, so the number of parameters over here will be 4,80,000 to 4,80,000, and there is one single output layer, which is, say, it's a house picture or a car picture, whatever. If that's the kind of decision that you want to take, so 4,80,000 into 4,80,000 plus 4,80,000 over here, that will come to approximately 230 billion. Right. So, and if you don't want that kind of numbers, if you keep only 1,000 things here, yeah, I mean, see, basically, like again, you can actually like so reduce it. 4,80,000 into 1,000 will be 4,80,000. That will be the dimensionality of the input into 1,000 plus another 1,000. So that will again come to around 480 million, which is also not very small. So how do you address this problem? We have a large parameter space, and we are looking at the case of an image classification problem. And if you want to handle problems of this kind, where the spatial signal that you need to consider, spatial signal is basically like a signal defined over the spatial dimensions of the input. So you have got a 2-dimensional what do you call image with 1 channel for each of the color. Meaning, like you have got essentially your data is a 3-dimensional data. and so the dimensions are 400 by 400 into 3. So for a problem which is as simple as this, and if you assume that you have got what you call a million data points, training points of this kind, so that's a kind of complexity that you deal with. How do you address this, right? Can you do a better what do you call better way of looking at this kind of problem, the image or spatial signal processing problem? And that is where convolutional neural networks came into existence. Let's see how a convolution layer can help. And I hope go back, if you're not familiar, go back, look at the convolution operator, and what is being defined as convolution over here is a little different from the actual convolution operator. So even though I don't want to call it an abuse of terminology, but it's a little different. So convolution is essentially like, what you do is essentially can you place a filter over here. So this is as if you want to see only see whether certain patterns do exist in this data. That's what it is, if you want to look at the semantics. And this is what the convolved image will look like, right? Inspired by the neurophysiological experiments conducted by Hubel and Wiesel in 1962. That's where convolution, this kind of context came into existence. So let me, rather than looking at the entire image, let me look at the image through certain filters, or let me look at the image through certain filters. Let us look at this as an example. So the convolution defined over here is, if this is your image and if this is your convolutional filter, the filter that you define, it's a 2x2 filter, where the weights of the filter are W1, W2, and W3 and W4. Basically, this is essentially the weights in the network. So you can presume this as like these dimensions connected to a neuron through these weights. That's what it is. All right, and the operation that it does is like it's the same thing. A1 into W1 plus A into W1 plus B into W2 plus etc. And then pass through a nonlinearity activation. So this is what the convolution operator is. Input image is convolved with the weights, essentially like the weights which are essentially representing the filter, the convolution filter, and then you're pushing through the activation, right? So the number of parameters, the moment you apply something of this kind, what happens is the number of parameters for one feature map is 4. So basically, like, this is called a feature map. Essentially, like you look at the image through a convolution filter, and this, what you get as output is called a feature map. So for a feature map, there is like four parameters. So it's a 2x2 feature map or a convolutional filter. So we got 4 parameters, which are essentially the 4 weights. And if I want to have n filters of this kind, say if I have 100 filters of this kind, so your parameters for this filter will essentially come down to only 4 to 100. So instead of what you can do is you can actually stride, meaning like, say you have a 2x2 or you have a 3x3 filter or 2x2 filter. You take you take the image and you stride, meaning you actually you actually take this filter through your image in a linear fashion, primarily like one after the other, layer by layer. Basically, like you take the first layer, then comes down, and this process is called stride. You stride over the image. And it can be as simple as, once you are done with, if a 2x2, so 2x2 is taken over here, and 2x2 stride till the right side of the image, and then you do this, like if the stride is 1, which means that at any step you do a 1 jump, meaning like X dimension, you do 1 jump. And if the stride is 1, which says that once you're done with the first row of things, first row of striding, then you do like 1 jump down and then do striding again. So this is called striding. So essentially, like you reduce each of these 4x4 thing into one value, right? That's what is happening in convolution. All right. Lower layers are more complex features. You have the image, and then you can actually like apply n layers of striding, or with multiple kernel functions, or essentially called the kernels, and you get feature maps, corresponding feature maps. So for example, if I've got 100 convolutional filters of this kind, all right, what you get is like you get 100 feature maps for one image, right? So and these 100 feature maps, each of these is a 2x2 filter. What you get is 2x2, 4 into 100. So 400 parameters, you get 100 feature maps for each image. right? And once you do that, but if you want to bring down your data, what do you call it, volume, you can see this is a typical operation called pooling. Pooling is essentially like you take what do you call a window of say 2 by 2 4, and you take max pooling. What you do is you take the maximum and this value. The max pooling of this particular window will be 5. You get you will return 5. Average pooling is you take the average of the values out there. So pooling is another operation. So average pooling reports the average value of the rectangular neighborhood. That's what it is. So out of this, max pooling will return 4. Out of this window, max pooling can return whatever. Right? It doesn't happen that way. It's basically overlap pooling. So you don't. If it is a non-overlap, out of this window you will get 5. So you essentially pooling what it does is it will reduce your data size. Right? The whole of convolution neural network. If you look at like this, what you can do is you will apply operations of this kind. Essentially, like you apply convolutions, right? Convolutions, then followed by pooling, some sort of pooling, then convolution pooling, and then you can once you have all this, you can actually do a flattening. Flattening is essentially like kind of you connect everybody to everybody. So that's a kind of operation. So basically, like flatten this what do you call that 2D into the 1D kind of representation. So and then you apply a what you call fully connected feed-forward neural network, which is very similar to your feed-forward neural network, and then you do the actual classification. So in short, and we'll be coming back and revisiting this topic again. I just wanted you to get started with it. Convolution neural network is essentially like the output can be a binary output, multinomial, meaning like doesn't have to be binary. It can be continuous output. It can be a count. It can be a classification context, whatever. And input is typically in a convolution network, you assume that the input is fixed size, right? And all right, architecture is your concern. I've given you a very simple sequential architecture. It doesn't have to be this particular kind of architecture. You go back, look at ImageNet problems, and you get a lot of architectures which are arbitrarily complex, right? Choice is yours. Optimization is again back propagation. Your convolution is nothing but the weights of the network, all right? And optimization is backpropagation algorithm, right? You can see it. Computing is typically use a lot of GPU power. Like before we wind up the session today, I want to show you how I remember I've shown you what do you call the context of a mask classification problem in the Google AI experiments long back. Let me show you that again with a little different context. Again, collab. Let's go to. I will share this code with you. So don't worry. So don't see a lot of it. Let me show you a CNN demo. So all I want to say is convolution neural network is essentially processing context. Let's go back to those slides once I see this. Once we see this. So again, I'm using a Keras model. Building a CNN. So I initialize, so I say like it's a sequential thing, one after the other. So I add two, in my network, I define in my network, and my problem is a mask detection problem. Mask detection problem, if you remember our old mask detection problem, what I have is, let me show my drive, Google Drive. I've got data there. I've got data in Colab, what do you call it? Colab notebooks. In my Colab notebooks, these are my data points. I've got pictures of. So I've got pictures of people with mask and without mask. I'll show you this data. You can see the data over here. So these are pictures I think I've taken from what do you call it? Different contexts. This is Kaggle data context. So this is my training data. This is the masked one, and there's a non-masked data. I've got 11 data points or something like that. This is something that I've polished. This is non-masked data points. You can see the images. I've got 10 or 11 data points out here, and I've taken a few other points for testing also. Testing, I've taken some points. I've got test 2. Basically, yeah, that's what it is. Some other picture, some pictures on that, right? So I've got some points in the test data also, and this is my CNN demo thing. What I've done is like I've created a simple CNN, a sequential CNN, right? And my CNN has what you call the first layer is a convolution layer. It's a 3 by 3 convolutional filter I use. I've got 32 such filters there. So I'm creating 32 feature maps using 3 by 3. This is a 3 by 3 feature map. Input shape is 64 by 64 by 3. Basically, just like the 400 by 400 by 3. Activation I use in the convolution is ReLU. And followed by a pooling layer, it's a max pool, 2 by 2 windows. Again, I add one more convolution layer, and you can, if you don't want to, you can actually experiment. I just did a basic experiment, and then followed by a flattened layer, so that I get a flattened 1D representation of the data. Once I have that, I have a simple densely connected network, a feed-forward network with a ReLU and SIGMOD. So the first, first network has, after the flattened layer, the first, hidden layer. Beyond that is a 128 neuron hidden layer. It's just for, I experimented with some data, with some parameters, 128 dimensional, network. So I've got convolution followed by max pooling, convolution, max pooling, flattened layer, followed by a, a 2 dense layer. The first dense layer is a 128 neuronal dense layer, followed by a 1 neuron dense layer, basically the output layer. Right? And then I compile the network, just like I've shown in the earlier class. Then I have just mounted my data, which is basically like mounted my Google Drive where the data is. I put the training, I've given the training, training directory, and then I've fit the basically like I've trained the network, and I'm I do a testing with the available data. That's what I do. Let me run this code and show you. This will ask for my since my data is placed in the Google Drive, this will ask for my permission. Let me go through that. I'll show you, and then we'll go back to the slide. All I want to show from this experiment is, it's asking for my authorization code because my data is in the Google Drive. Right? So I have data over here. Need to give permissions, allow. Since my data in the Google Drive, that's where I am. They're asking for my, I've copied the code. It's basically when you put your data in the, the Google Drive view, you have to give the permission like this. Paste it. And given the permission, so it must be running by now. Yeah, authorization code is there. So it started working. Now the mounting happened, meaning my Google Drive is mounted, and the data, there are 22 images belonging to 2 classes. The images are belonging to, as you have already seen, it's in the in the class of mask and on. The predict is no mask. What was the image that you tested? What was the image? Let me look at the code. Not this one. I was testing test0.png. Test0.png. Test0.png is a no mask thing. So it is predicted to be right. What are the other things? Let me test1.png. What is test1.png? No, we'll check another one. Text4.png. Let me test that. I could have actually put it in different buckets so that the life would be easier. Test4.png is actually it's predicted to be wrong, right? You see that? So it's predicted to be a no mask. So likewise, I can test it another test6.png. What is test6.png? It's a mask thing. Test6.png. Yeah, it's mask. Test6 is predicted correctly. It's a masked one, masked image. So Test6 is corrected. So I mean the problem is not completely solved. So I mean not test the accuracy. Accuracy maybe around 80, 90, whatever. Right? So all I want to show is building a convolution neural network with TensorFlow and algorithm is not very difficult. All we have, I've created a network with two convolution, two layer sequential convolution followed by, convolution and pooling followed by a flattened layer, and then there is a two dense layer, and we have applied that to solve a problem which is very interesting, right? The mask detection problem. Right? So all I want to show here is yes, solving such problems with convolution neural network is pretty straightforward. You start exploring ImageNet classification problem and start looking at the network. And we will be like kind of once you have done with your basic exploration of CNN, and some of you can take up this as your mini project. What do you call introduction to convolution neural network through an example, right? So basically a tutorial on convolution network through an example. So let's go back to our original context. So what does a convolution neural network do? A convolution neural network is essentially is a deep neural architecture which can do spatial signal processing. And so what it does is it can take it can take a raw input, apply convolution followed by operations of this kind called max pooling or pooling. Then you can have as many convolution pooling layers, and then you essentially do a flattening to get a vectorial representation of the output, and then you get a one-dimensional representation. Then there is a fully connected network which does your machine learning, primarily this is the machine learning part. There is a feature engineering part, this is the machine learning part. That's what convolution network is all about. With that, and there are interesting terms in the convolutional context. One is called as striding. Striding is essentially like how do you move your filter, right? How do you move your filter across an image, right? Striding 1,1 meaning across X, you do one shift, and once you're done with the entire horizontal line, you come down one shift. So 1,1, that's what it is. 2 by 2 meaning like you do two shifting, right? So basically like you 2 here and jump 2 position, and likewise 2 by 2. So 2 by 1 is basically like, so that's a way in which you do, that's called striding, the concept of striding. There's another interesting concept in the case of convolution neural network. This is called pooling. It's called padding, P-A-D-D-I-N-G. Padding is essentially like, sometimes you have an image of this kind. So you have so basically 1, 2, 3, 4. So it's a 16, 4 by 4, 16 is the size of the image, 4 by 4, 16 values out there, right? You may want to you may want your output also to be a 16 dimensional thing. So what you can do is you can put zeros around it. Right? You can pad your image with zeros, so that your output size is the same as that of the input size. So, and in TensorFlow and Keras, you can actually give padding with same size or whatever, and there is a parameter there. Then what you do is you can do that. So padding is another interesting aspect. Otherwise, convolution neural network is all about understanding what a convolution is. Using convolution, you do feature engineering. You reduce your data size using pooling, and then we have to specify a stride parameter. Essentially, how do you move the filter across the image, and then you have to specify whether you need to do padding or not. Otherwise, that's all. These are the concepts that are the most important ones in the case of convolution network. Once you understand these concepts, you'll be able to understand what convolution network is. To summarize, what I want to say is convolution neural network is essentially a deep learning architecture originally proposed for image processing problems. But now people have started applying that. Not started actually. People have successfully applied that in text processing problems also, or even problems beyond image processing. Don't think that convolutional network is same means all about image processing. It finds most of the early applications in image processing, but this is finding much more sophisticated and interesting applications in the other fields also in the recent times. With that, I'll probably stop the recording of this session, and then we can have a discussion further down on this.